We're surrounded by all these incredibly complex systems, planes, power grids, chemical plants. We basically trust them with our lives every single day. But have you ever stopped to ask, what's the actual plan for when things go wrong? Well, today we're going to pull back the curtain on safety engineering. It's this amazing, invisible architecture that's designed to prevent disasters. Because here's the key. It isn't just about reacting to disasters after the fact. No, the real genius is in this super disciplined, proactive mindset that asks this very question. It's all about designing failure right out of the system from the very beginning. And that whole mindset, it's got a name: safety by design. Think of it like this. You don't build a massive skyscraper and then try to figure out how to make it earthquake-proof, right? Of course not. That strength, that resistance, it has to be in its DNA. It has to be woven into every single beam and every single blueprint from day one. And that's the core idea we're going to dive into today. So here's our roadmap. First, we'll start with that foundation, designing for safety. Then we'll put on our detective hats and figure out how to find potential hazards. After that, we'll see how one tiny failure can spiral. We'll learn how engineers actually put a number on risk. And finally, we'll tackle the most unpredictable part of any system, which, of course, is us. All right, let's get started right at the beginning, at the very foundation. So, every safe design has to begin with this crucial next step, basically playing detective. Once you've got a blueprint, how do you go about systematically hunting for all of its hidden weak spots? Because this isn't about guesswork at all. It's a really structured investigation. And it really comes down to a kind of formalized curiosity. Engineers use these powerful tools, like HAZOP, where they just systematically ask, what if, for every single stage of a process? What if the temperature gets too high? What if a pipe gets blocked? And then there's FMEA. That's where they zoom way in on just one specific component, like a single valve, and they brainstorm every conceivable way it could fail, and then map out all the ripple effects. Okay, so now we've got a list of all these potential failures. But how do those failures actually connect to a real-world disaster? Well, now it's time to connect the dominoes. So, engineers think about this in two opposite but totally complementary ways. First, with fault tree analysis, you act like a detective. You start with a catastrophe, let's say a huge explosion, and you work backward, mapping out every single combination of smaller failures that could possibly have led to it. Then, with event tree analysis, you're more like a fortune teller. You start with just one initial problem, like a power outage, and you map forward to see all the possible outcomes, both good and bad. And there's this really powerful model called the bow tie that actually lets you visualize this whole chain of events. It all starts over here on the left, where you list every potential threat or root cause that could kickstart a problem. And all of those threats, they point right toward the center, to the knot of the bow tie. This is what's called the top event, that single critical moment where control is lost and the system fails. And then, from that one single event, the diagram branches out to the right, mapping out all the potential consequences and outcomes. So in one simple picture, you've got the entire story, from the causes to the critical failure to the ultimate impact. Pretty cool, right? But, just knowing what could happen isn't really enough. To decide where you're going to spend your time and your money, you have to move from just asking what if to asking how likely and how bad. You have to actually quantify the risk. And that is the job of something called quantitative risk assessment, or QRA. This whole process uses historical data, uses statistical analysis, all to put a hard number on risk. It answers questions like, is it more likely for this specific pump to fail or for that pipe over there to burst? And by quantifying the risk, engineers can stop guessing and start making truly objective, data-driven decisions on where to focus their energy. This brings us to a really subtle but absolutely critical distinction. Safety is not the same thing as reliability. Reliability just means the system works like it's supposed to, like your car's engine starting every single morning. That's reliability. But safety means the system doesn't cause harm, especially when it fails. Your car's airbags are a perfect example of a safety feature. They only work during a failure, a crash. This means a system can actually be safe but unreliable, or, way more dangerously, it can be reliable but completely unsafe. Okay, let's move on to the final and, let's be honest, often the most challenging piece of this puzzle. You can have the best design system in the entire world, but at the end of the day, it's going to be operated and maintained by people. So how do you count for the human factor? The modern approach isn't about blaming people for making mistakes. It's about accepting that human error is just inevitable. So the goal completely shifts. Instead, you design systems that are resilient, systems that can catch an error or maybe absorb it without it leading to a catastrophe. Think about the guards on a power tool, or that little confirmation screen that pops up before you delete a file. Ultimately, all of these tools have to exist inside a much larger culture of safety. And that means investigating accidents to learn from them, not just to point fingers. It means putting in place formal management systems like OSHA MS to make safety a daily, documented process. And it means using cutting-edge technology, like virtual reality, to train people for those super rare, high-stakes events they might otherwise never experience until it's way too late. So, from proactive design all the way to accounting for human error, that's really the architecture of safety engineering. It's a systematic effort to stop things from going wrong long before they ever happen. So the next time you board a plane or you cross a bridge, just remember all the layers of invisible thought that are working to keep you safe. And so now, looking at your own world, I've got a question for you. What risks do you see differently?